My name is Reagan Wakefield, and this is my Physics 2211 Oscillations Lab. The purpose of this lab is to investigate a mass spring system by examining the motion of an object swinging in an arc while oscillating on a spring. We will do this by analyzing a given video and tracker to extract the position data of the object. The position data will be saved as a CSV file and called in our GlowScript code. In GlowScript, we will plot the motion of the mass through a position versus time graph, compare the predicted and observed motion of the mass, and plot the energy changes computed in the model. The first fundamental physics principle used in this lab is Newton's second law, which states that force is equal to the change in momentum over the change in time. The second principle is Hooke's law, which states that the force needed to extend or compress a spring by some distance scales linearly with respect to that distance. Finally, the energy principle states that energy cannot be created nor destroyed, but it can be transformed or transferred. We will be using numerous formulas for this lab. The first formula is Newton's second law, which states that net force is equal to the change in momentum over the change in time. From Newton's second law, we derive two other formulas called the position update formula and the velocity update formula. These formulas predict the future position and velocity of an object based on initial condition. The energy principle states the change in energy equals the work done by the surroundings plus heat. However, since there isn't any heat in this lab, we can reduce this formula down to delta E equals W. In this specific lab, we are taking the mass, spring, and earth as our system, so there's no work done in the surroundings. Thus, the change in energy can be defined as delta K plus delta U grav near earth plus delta U spring. All of the formulas to find these values are listed on this slide. As I mentioned earlier, the system will be the mass, spring, and earth, and the surroundings will be nothing. And as we will see later on in the presentation, the change in energy will be around zero. However, the predicted and observed models will differ and not line up perfectly. I used this provided video and tracker to track the motion of the object and plotted the X and Y positions for each frame. I chose my axis so that up is positive Y and right is positive X. Here are some excerpts of my code showcasing the initial conditions. I set the mass equal to 0.402 kilograms as that it was provided to us. From the tracker data, I obtained the initial position of 0.022 in the X direction and negative 0.701 in the Y direction. I also set the initial velocity equal to 0 because the mass begins at rest. I set G equal to the gravitational constant 9.8. I then obtained the spring constant K and relaxed length of the spring L naught through calculations that can be seen on the right of the slide. From the tracker data, I obtained T, the period of oscillation, to be 1.52 seconds. I then rearranged the equation T equals 2 pi times the square root of M over K to find a formula for K. Plugging in my T value, I find that K was equal to 6.87. Finally, I used the equation L naught equals L minus mg over K to find that L naught equals 0.127 meters. Next, I created the equation for the length, which was the position of the object minus the position of the spring. L hat being L over the magnitude of L, and S being the magnitude of L minus L naught. Then I used the equations for kinetic energy, gravitational potential energy, and spring potential energy, and added them all up to find the total energy. I then calculated the force due to gravity and the spring force from the equations shown in slide 3. I then set the net force equal to the sum of these two individual forces. I updated the ball's position and velocity using the position and velocity update formulas. I also updated the spring and recalculated L, L hat, and S. Finally, I calculated the energy changes and solved for delta K, delta U, and delta S. I added up these energies to find delta E. This is the resulting change in energy versus time graph. As we can see, the total change in energy, the orange line, stays at around 0, suggesting no change in the total energy for the entire motion of the mass. Delta K and delta U graph both oscillate. Here's the predicted versus observed graph that I obtained. As you can see, the predicted and experimental lines don't match up to each other. This could be for a variety of reasons. One being that I calculated the spring constant using the period of oscillation from the data from the Y position, which may not line up with the X position data. The first follow-up question is the energy principle satisfied? Earlier, we said that no work is done in the system. By the energy principle, the change in total energy equals the work done by the system. If no work is done, then the change in energy equals 0. This is represented in our change in energy versus time graph, as the orange line remained at around 0. Therefore, the energy principle is satisfied. The second question is to make two different estimates of oscillation periods, one from the X position data and tracker, and the other from the Y position data and tracker. I found that the oscillation period from the X data equals 1.61 seconds, and the oscillation period from the Y data equals 1.52 seconds. This impacts the results because T is used to calculate the spring stiffness. This impacts many other calculations that are used to estimate the motion of the object. In my calculations, I use T from the Y position data because the spring is in the Y direction. Finally, some sources of error that I may have had in this lab could be human error with glow script and tracker, as I could potentially have small errors. In addition, as I just mentioned, there could be a discrepancy between the differing oscillation periods for the X and Y data. This discrepancy could have impacted my calculations and results. Thank you so much for watching this video. I hope you enjoyed.